Hey everyone, welcome back to Bug no Jutsu, your go-to place for understanding coding problems with simple explanations. In today's video, we're going to discuss a really popular LeetCode problem called Valid Sudoku. It's a neat problem that combines logic with careful checking, and by the end of this video, you'll have a clear understanding of how to approach it. So, the problem goes like this: we're given a 9 by 9 Sudoku board, and we need to determine if it's valid according to the Sudoku rules. Remember, a valid Sudoku board means each row must contain the digits 1 to 9 without repetition. Each column must also contain the digits 1 to 9 without repetition. And finally, each of the 9 3 by 3 subboxes inside the grid must also have the digits 1 to 9 without repetition. It's important to note that the board we're checking might not be fully filled. Some cells can be empty, represented by a dot. Our task is not to solve the Sudoku but just to validate whether the given arrangement so far follows the rules. For example, let's take the board given in the problem statement. If we pass that board into our function, it returns true. This means the current placement of numbers doesn't violate any Sudoku rule. That's enough for us to know. We don't need to check every detail of the example here, because the output confirms that the given Sudoku setup is indeed valid. Now, let's talk about the approach I used. We want to keep track of 3 things while scanning the board: the numbers we've seen in each row, in each column, and in each 3 by 3 box. To do this efficiently, I used sets, which allow us to quickly check if a number already exists. Here's the step-by-step idea. Loop through every cell in the board. If the cell is empty, we just skip it. If the cell has a number, we check 3 conditions. Is it already present in the current row? In the current column? Or in the current 3 by 3 subbox? If it's found in any of these, that means the board is invalid, and we can directly return false. If the number is not found, we add it to the respective row, column, and box set, and keep going. If we finish scanning the entire board without any conflicts, that means the Sudoku is valid, so we return true. This approach is clean, avoids unnecessary complexity, and ensures we check all the rules in one pass. The time complexity here is 1, because no matter what, we're always scanning through a 9 by 9 board, which has at most 81 cells. That's constant. The space complexity is also 1, because we're just storing at most 81 values in our sets, which again doesn't grow with input size. So this is very efficient. The valid Sudoku problem is a classic example of constraint validation. Instead of solving the puzzle, the challenge lies in ensuring every row, column, and 3 by 3 subbox respects the uniqueness rule for digits 1 to 9. Using sets makes this efficient since each lookup and insertion is 1, allowing us to quickly detect duplicates without repeatedly scanning rows and columns. A key trick is mapping each cell, R, C, to its subbox using R divides 3, C divides 3, which generalizes well to many grid-based problems. This highlights the importance of hashing, efficient state tracking, and reducing multidimensional checks into simple keys, insights that extend beyond Sudoku. The techniques here have wide-ranging applications in both algorithms and real-world scenarios. Many constraint satisfaction problems such as crossword validation, n-queens, or even scheduling tasks benefit from the same uniqueness checking strategy. Grid problems like battleship validation, word search, or matrix operations reuse this pattern too. And that's it for today's video. We went through the valid Sudoku problem, explained the rules, walked through an example, understood the solution, and discussed the complexity and insights. If you found this helpful, make sure to hit the like button, subscribe to Bug no Jutsu, and share this video with your friends who are also practicing coding problems. Thanks for watching, and I'll see you in the next one.